In this example, we consider a differential equation that is dependent upon both x and y. Part A. On the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. So we see a graph here with the 12 points indicated. Because this differential equation is dependent upon both x and y, we have to consider using both values at each of these points. I can do some thinking about what would be easiest and consider that because I'm multiplying this x term times this y term, if I make one of them 0, 0 times the other one results in 0. So I could think about when x equals 0 and not have to worry about what y is going to equal because dy dx equals 0 squared times y minus 1, which will be, no matter what y is, equal to 0. So when I go to graph the slope lines, anywhere x equals 0, it's going to be a slope of 0. So a little horizontal segment at each of these places where x equals 0. I can also get 0 for a slope if I make the y equal to 1. So let's consider when y equals 1, that dy dx equals, now I didn't pick anything for x, so I leave it as x squared, 1 minus 1, which is 0, and that, of course, is going to make 0. So any place where y equals 1, which is up here, is going to be a horizontal line segment. So I'm looking for patterns, things that help me to make this slope field turn out easier. Another pattern is because x squared, or because x is squared, it doesn't matter when I pick x equals 1, if I pick positive or negative 1, it will turn out the same. So let's say when x equals positive or negative 1, and we do need to pick a value for y at this point. So I'm going to say, instead of just picking the x, let's say at the point plus or minus 1, and then the y coordinate 0. So at these points, I also need a slope value. So whether I'm doing positive or negative 1, when I square it, I get 1. Plugging in 0, 0 minus 1, I get 1 times negative 1, which is negative 1. So at positive 1, 0 here and negative 1, 0 here, I have a slope of negative 1. Remember, we do our best to show that it's a negative slope with approximately a rise over run of down 1 over 1, and that looks about like this. What other points are left on the graph? How about when x is 1 and y is 2, and when x is 1 and y is 3? So we still have to find out what it is at 1, 2 and at 1, 3. So let's do those two slope values as well. Again, plus or minus 1 is going to be squared, and then 2 plugged in gives me positive 1. So at the 1, 2, it's a positive 1 slope, and at negative 1, 2 as well. Then at 1, 3, the derivative dy dx is 1 times 3 minus 1, which makes 2. So a slope of positive 2 at both of these points, which means just a little steeper than that slope, which was positive 1. And there I have the slope field for that given differential equation. Part B. While the slope field in Part A is drawn at only 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. Well, remember that we're using dy dx to find our slopes. So when they say we want the slopes to be positive, we want dy dx to be greater than 0. Well, if dy dx equals x squared times y minus 1, we know that this is always going to be positive as long as we're not plugging in 0. So even though x squared is greater than 0 always, sometimes it could equal 0. So we just want to make sure that x is not equal to 0. This is one of the ways to describe some of the points. But of course, we also have to think about the y coordinates. So as long as this is also positive, since x squared is going to be positive, so y minus 1 has to be positive, greater than 0. Therefore, adding 1 we know that y has to be greater than 1. So the ways to describe the points is that x can't equal 0 and y has to be greater than 1. Both of these have to happen to get the slopes to be positive. Thanks for watching.